This made me laugh more than it should. You've got infinity times this kind of 2 by 2 grid of numbers equals 8. So what does this actually mean? Well, really, what Matt Parker is telling us here is that he's a nerd. So in this video, I'm going to explain what it actually means so that instead of crying, you can actually laugh along like Matt Parker. The important part of this equation is this matrix in the middle. This is where the magic happens, and it's actually a lot more complicated than it looks. So what actually is a matrix? Well, if you've got an x and a y axis and vector A equals 2, 3, then that means to get vector A, you go 2 across and 3 up. So vector A looks like that, and if vector B is -7, 1, then you go -7, which is all the way that way, and then +1, which goes like that. So vector B is like this. But what exactly is a matrix? Well, we can take a matrix and multiply it by a vector to get another vector. So if we multiply 1, 0, 0, 1 by 2, 3, how we do that is we take the first row and we multiply it by the first column. Okay? So we take 1 multiplied by 2 and we add 0 multiplied by 3. So 0 times 3 is 0, 1 times 2 gives us 2. So in here we put in a 2, and then next we've got the second row multiplied by the column again. So in this case we've got 0 times 2 plus 1 times 3, which is equal to 3. So 3 goes in here. Basically all we've done here is nothing. 2, 3 turns into 2, 3, so this matrix does nothing. It's called the identity matrix, and it's the same as the identity element in multiplication, which basically when you multiply it by anything, you just get the same thing. Just like when you multiply 1 by anything, you just get the same thing. So what about if we multiply it by this matrix? Well, we get -1 times 2 plus 0 times 3, which is just 0, and that gives us -2. So we get -2 in here. And the next row multiplied by the same column is 0 by 2 plus 2 by 3, which is 6. So what we're really doing here is we're taking the top row and multiplying it by -1 to get this. So we just get -1 times 2 equals -2. And 2 times 3 equals 6. And if I show you what that looks like on a grid, it's like going 2 across and then 3 up and giving us vector A. And then instead of that, we go -2 along and then 6 up, which gives us vector A prime, which is the image of A. Now you can't actually see this, but what we've really done is reflected it and then stretched it up, okay? And if you do this with any other vector, the same matrix. So basically what this matrix does is takes the first coordinate, which is the x coordinate, and multiplies it by -1, which flips it, and then multiplies the y coordinate, which is this one, by 2, so it stretches it in the y-axis. So what we get is an image of whatever we put in here to be flipped in the y-axis and then stretched along the y-axis. So what the hell does this matrix actually do then? Well, it's a little bit more complicated than it looks, because if we multiply it by any general point x, y, which is our x coordinate and our y coordinate, then what we end up with is 0 times x plus -1 times y, which is -y, and then 1 times x plus 0 times y, which is just x. So we basically flip the coordinate around and then make the first one negative. Okay, so let's say we've got an axis, and let's say we've got a point x, y, and I want to rotate this point at an angle theta anti-clockwise around the x-axis. Okay, so what this means is we take this point xy, which is a vector, okay, and then we rotate it by an angle which is theta around the origin, around the center. Okay, so try this one on for size. Let's say you've got the xy coordinate, which can be represented by the vector xy, obviously, and you want to rotate it this time, rather than just stretching it, you want to rotate it around the origin anti-clockwise by an angle of A. Now, you might think that that's impossible, but it actually is possible with matrices, because remember, we've only been multiplying by matrices where this and this is equal to 0. We've not been actually considering what these other two values could be. So have a think about it. You can pause the video now to try it out for yourself. Okay, so let's say you've got a coordinate grid and there's a point here, which we'll call A. So if I connect that up there, let's call this point, point X, Y, which obviously will have the vector X, comma, Y. And then let's have another point, which we'll call it, well, we won't give it a name. We'll just put it somewhere up here. Okay, so to get to this point, we want to rotate X, Y by an angle of A. Okay, so this is the rotation of XY. Do you get it? Alright, you little pleb. Okay, so let's say you've got a point X, Y, and we want to rotate it anti-clockwise about the center by angle A. Okay, and let's call this angle here B. Alright, so you're going to need to know trigonometry for this. I know, right? How fun. Let's get into it. So I'm going to make a right angle triangle like so. So this is our right angle, okay? Now this, okay, is not a right angle triangle because this length is equal to this length. So we're going to draw it down to the ground here. So now it is a right angle triangle like so. So we've got two right angle triangles. You get me, right? Now we know that this point here has just been rotated around here. So the length from the green to the purple line hasn't really changed. So we're going to call them both H because that's the name of the hypotenuse, H, okay? And so we can say that this length here is going to be Y because the Y coordinate is the vertical. We can say Y is equal to H multiplied by sine B, because that's going to give us the opposite side. So H sine B. And we can say X is equal to H times cosine B, okay? And we can say that this here, we'll call this capital X, capital Y, because that's our image, right? So capital X, capital Y, which is our new value for our XY vector. We can say that capital X is equal to H times the cosine of A and B. And we can say that capital Y is H times the sine of A and B. Okay, so all we need now is the double angle formulas, alright? So cosine A plus B is actually the same as cosine A cosine B minus sine A sine B, and sine A plus B is actually the same as sine A cosine B plus sine B cosine A. So we can use these double angle formulas to simplify these. So X is now H times the cosine A and B, which I'll just copy it down now, and Y equals H times the sine A and B, which is sine A cosine B, plus sine B cosine A. Okay, so this looks more complicated, but trust me, it's not, because remember, Y equals H sine B and X equals H cosine B. So we can divide both of these equations by H, and look what we get. We get sine B equals Y over H, and cosine B equals X over H. So we can replace the sine B and the cosine B by Y over H and X over H, and we get, okay, so I've replaced sine B and cosine B with X over H and Y over H, and now you can see that these H's, which are multiplied out, get cancelled out by the denominators, so H, 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 and we get X equals X cosine A minus Y sine A, and Y, capital Y, equals X sine A plus Y cosine A. Okay, so what was the point in all of that? Well, now we know to rotate a point XY to capital XY, you use this equation, these two equations, but there's another way to represent it, and that is using a matrix. You see, if we take the matrix cosine A, and then minus sine A here, and sine A here, notice what happens. If we multiply it by a point x comma y, then we get x times cosine A, and then you've got this one here is minus y times sine A. Then we've got x times sine A plus y times cosine A, which is the same as that. So this is a rotation matrix. This is how you rotate something as a matrix. Now, back to the original problem. Notice something about this, yeah? You see this? You see this? This is being rotated, all right? Okay, now, how much is it being rotated by? Is it being rotated by 180 degrees? Is it being rotated by 360 degrees? Is it being rotated by... It's being rotated by 90 degrees, okay? And watch what happens if we put A equals 90 degrees, we get sine A equals 1 and cosine A equals 0. So we get the matrix 0 and then 1, minus 1, 0. And that is the rotation matrix by 90 degrees. So what this is saying is that you rotate a matrix, you rotate the image by 90 degrees, because if this is an image, yeah, and it's a bunch of points, then you rotate it by 90 degrees, okay? If you enjoyed that video, join the channel to pay for my therapy, click on this video if you want to see more, and piss off.